Let's have a look at friction. Tried to record this in the Zoom meeting yesterday and it didn't work, so we'll give it a shot here. This is a picture from your textbook and illustrating how friction can arise. And it's got a crate here sitting on top of some sort of a surface, and maybe you're pushing or pulling on this crate to try to move it to the right. And if you look at a very blown up view of the bottom of the crate and the top of the surface, you'll see something like this. They're typically not smooth at the microscopic or submicroscopic level, typically at the atomic level, and things can get bumpy. And when you try to move the top thing sideways with respect to the bottom thing, you'll have to overcome repulsion between some of these atoms, attraction between some of these atoms, and things can get kind of crazy. They mention in the description of this thing, even perfectly smooth surfaces are not friction free, and they mention perfectly smooth clean surfaces of similar materials would adhere, forming a bond called a cold weld. I don't know if you've ever done this before, but if you have two sheets of glass that are laying right on top of each other, it's actually difficult to lift one of them off the other because of attraction between the atoms. Then it's difficult to slide one relative to the other. So that's kind of a thing that happens. Now, this is going to be really complicated to try and analyze. Atoms are tiny. And on the back of this sheet, just for the heck of it, I drew a centimeter, 1 centimeter squared. And atoms are, whoops, that's a C. It may look like a K, but it's 1 centimeter squared. Anyway, atoms are small enough, typically nanometer sized for an atom. So in a centimeter long length of something, you might have 10 to the 7th atoms along there. And you'd have 10 to the 7th atoms along here. Okay, well, 10 to the 7th times 10 to the 7th means in a little area like this, you might have 10 to the 14th atoms in there of one surface, and above it 10 to the 14th atoms of another. That's just rough estimates, but that's a lot of atoms, and there are going to be attractions and repulsions between many of those things. There's no way you would ever want to attempt that. And so what we have done instead is to deal or develop experimentally some ways that frictional forces appear to act. And if you've got two surfaces and you do enough experiments, you'll find that there are actually two types of friction. There's static, and that's before movement occurs. And with static friction, what happens is that you've got one surface here, and you try to push something, exert a force on something with respect to that surface, and you push, nothing happens, push a little harder, nothing happens, push harder and harder and harder, and eventually you'll get the thing to move. That static frictional force is a variable force, but it'll have a maximum value, and eventually you'll get the thing to move. And experimentally we have discovered that the magnitude of a frictional force, and it's not very precise, but it's the best we can do, is proportional to the normal force. Now, this is the Greek letter mu, just mu, and it's pronounced like the noise a kitten makes anyway. I've got a subscript of an S on it because it's static friction, and actually it's not equal to that. it's less than or equal to that. So it has a maximum value is when that's equal. And so when that's the case, we'll say that the static friction is maxed out. And most of the experiments or the problems that we'll solve will be interested in doing that. Interesting thing, it depends on the normal force between the two objects. Okay, well, that's a force that the bottom surface is exerting on the top. That's where the normal force acts. However, there is a third law partner of that normal force, which is the force that the top surface is exerting downward on the bottom, and that's the one that actually gives rise to the friction. So there we have it for static friction. Then there's kinetic friction. And that's when sliding is going on. Okay, and kinetic friction, we can just have an equality on that one. It's another different constant, mu sub k, and again it's proportional to the normal force that acts between the two surfaces. So we have it looking like that. Now, where did I put those coefficients of friction? Here they are. I think this is out of your book. Some various coefficients of friction. Not many significant figures on these. Once in a while you'll get two significant figures. Most of the time you only have one significant figure on the coefficients of friction because there's so much variability on these things, and it's a complicated thing to measure. Wood on wood, 0.5, something like that. Okay. Waxed wood on wet snow. There's been a lot of research of waxed wood on different types of snow. The ski industry supports that sort of research. So metal on wood, all kinds of different things. Steel on steel, oil, that's quite a low coefficient of friction. And so you can get things like that moving pretty well. Teflon on steel. Actually, this is a rare one where both the static and the kinetic friction are the same thing. Teflon is a very low friction material. It's not just in fry pans anymore. In fact, the big blue telescope we have at school has Teflon bearings, and I'll show you those sometime when I remember to. Ask me about it next Tuesday maybe. Bones lubricated by synovial fluid. Okay, 0.016, that's quite low, and kinetic friction is quite low. You don't want a lot of friction in your joints when you're moving, so you'd like to have that. Shoes on wood, things like that. Shoes on ice, pretty low coefficient of friction. Once you start sliding, it's even lower. Typically, the kinetic friction coefficients are lower than the static friction coefficients. And I'll talk about that when we get to a problem. I have another table. I'm not sure. This has some different values. Synovial joints in humans. Let's see. Yeah, just one significant figure, and they have different values on here. So depends on how it was tested and things like that. Teflon on Teflon, 0.04, 0.04. Teflon on steel, same thing. So Teflon is a particularly interesting thing. Unfortunately, Teflon wears off of your fry pans and probably goes into your scrambled eggs. So over time, you're eating a little bit of Teflon, which isn't the greatest thing for you probably. But people don't do research on the effects of that because it's sort of inhumane. Occasionally, very rough surfaces, you'll have coefficients of friction that are actually more than one. An example I can think of this is, I don't know if I've ever seen one of these in Washington State, but on highways that have long downhill stretches, a lot of times there will be runaway truck lanes, and one of the ones that I can remember is, or that I know of, is on Interstate 84 down in Oregon, east of Pendleton. Actually, as when you're going up the hill, they don't have these, but when you're going down the interstate, and they're the east and westbound lanes of the interstate are separated by quite a large distance, so you can't even see each other. But if you're doing the downhill part, there are two spots where there are runaway truck lanes there, and I've seen those a lot. I used to live in La Grande, Oregon. My first 2 years out of grad school, I was teaching there, and anyway, on those runaway truck lanes, the regular lane will be coming down here at some slope, and then off to the side they'll have a runaway lane for trucks that on that one, they don't always have them go uphill. Sometimes they're just the same slope, but they'll have that runaway truck lane filled with soft gravel. And when a truck has lost its brakes on the downhill descent, rather than just having them run away forever, they'll have a place where the truck can drive onto this soft gravel. And it's soft so that when the truck hits it, the wheels actually sink into that stuff, and they stop the truck in a very short length of time or length of distance. And that's a place where you'd have a coefficient of friction that's more than 1. And once a truck gets into there, a lot of times they can't get out. They'll have to have a tow truck come and pull them out of that soft gravel. And if no damage has happened to the truck, they'll be able to get back on the road and drive down. What happens is if the truck driver at the top of the hill hasn't put the truck into a low enough gear so that the engine will slow the thing down, then they'll have to ride their brakes on the way down, and brakes on trucks and cars get hot when you're having to use them continually, and the brakes will reach such a temperature that it can turn the brake fluid from a liquid into a gas, and then it doesn't make the brakes compress and stop the truck anymore, and so things aren't so good. Anyway, it's a complicated process. All right, well, let's try out some problems and see what we can do with these things. Let's see. All right, I know this is something you've all wondered about. Is the coefficient of static friction between an oiled non-stick fry pan and a frying egg is 0.040, what is the maximum angle at which you can tilt the pan before the egg starts to slide? Okay, static friction, maximum angle. We're trying to max out the static friction in this case. So static friction in general looks like F sub s is less than or equal to mu sub s times n, but we're trying to max it out. So in this case, the static friction will equal mu sub s times n. And we need to draw a free body diagram for this thing, but let's make a sketch first. Maybe this is the fry pan here, and inside of it we've got this egg. Somebody wants their egg sunny side up, and it'll be tilted like that. So this will be tilted with respect to the horizontal by some angle theta, and it's the maximum angle you can tilt it. If you go beyond that, all of a sudden the egg starts to slide down the pan, which may be something you want it to do, because then you can do a little chef's thing and flip the egg using the pan and not having to use a spatula. So big fun. All right, well, let's make a free body diagram over here. And a freebie force almost always is mg, straight downward like that. Now in this case, we've got this pan that's tilted here, and the normal force is going to be pointing up like this. And then the egg will tend to slide down the pan friction is in a direction opposing the sliding that would occur. So that's the direction of the frictional force. And I'll just put a subscriptive S on it for a static frictional force. And this is the angle theta. This is a situation where the sliding has not yet occurred. If we go a smidgen past that angle theta, it will occur. And so we just have these three forces acting and no acceleration yet. So Newton's second law in vector form, which usually looks like the sum of the forces is equal to ma. Well, in this case, that's going to be 0. So the forces add together to give me 0. I'll have N plus F sub S plus mg is equal to 0. And this is one of those three vector problems where I can draw a picture, not have to break things down into components, but I can draw a picture and solve the problem. I'm just trying to maximize this angle here. Well, let's see. What can we do with this picture? If I actually draw N first and then F sub S, here's what it'll look like. N is up at that angle like that. I'll make a big picture. Well, maybe not that big. And then F sub S is perpendicular to the normal force, so it's going to be up like this. And it's going to be a fraction of the size, 0.04 times, actually 1/25 the length, but I'm going to exaggerate it so I can draw a nicer picture. And then coming down here is mg. So there's the mg, here's the N, and here's the static frictional force. Now, this is a right angle. Let's see, how will I figure this out? This angle here. Oh, actually, I think I can get it. Yeah, this is theta, this is 90 minus theta, that's theta again. This is theta, this is 90 minus theta, and this would be theta again. And monkey around with that. See if you can get so you're figuring those out. I'll blow it up here a little bit. The angle between the fry pan and the horizontal is theta. This is a right angle here, which means this is 90 minus theta. That way this angle plus this one are 90 degrees. And this is another right angle here, so this will be theta again. That way this one plus this one will still equal 90 degrees. So do tricks like that. At any rate, this ends up being the angle theta. Now, I've got vectors drawn here, but this triangle is going to work even if I'm just dealing with the magnitudes of these vectors. And so the tangent of theta here will equal F sub S over N. Well, let's see what we get out of there. F sub S divided by N is the tangent of theta. F sub S is mu sub S times N when we max it out, so we'll have mu sub S times N divided by N is equal to the tangent of theta. I didn't even have to deal with the mass of the egg here, okay, because the N's divide out. They're going to be some mg cosine theta probably in this case, something like that. We'll do somewhere we figure that out, but tangent of theta equals mu sub S. That means theta is going to be the angle for which the tangent is mu sub S. So inverse tangent of 0.040. That's a number with only two significant figures, and I may have fudged that when I wrote this problem. I took it out of some book. They may have only had 0.4, but I don't remember. Or 0.04. Whatever that comes to. Not much. Okay, 2.3 degrees. And if it was just 0.04, you'd estimate about 2 degrees. Okay, well, you can't probably judge that easily with your eye, but so your egg will slide in the pan at a pretty shallow angle if you've got a nice brand new Teflon pan and you've oiled it. So, on to another. Okay, coefficient for the value of the static friction between worn tires and a road is 0.3. Now that's only one significant figure on that coefficient of friction, so we're not going to have a lot of precision when we solve this problem. If a car is traveling at 70 miles an hour, find the shortest distance in which the car can stop, and assume the static friction is maxed out in this case. You may wonder why we're using static friction for this particular situation, and find a piece of scratch paper here. Here's the reason. That's supposed to represent a wheel, and let's suppose that the car is traveling in this direction, and so the wheels are rolling like that. This point of contact between the tire and the road isn't just a single point. The tire actually flattens out a little bit, and so there's some area there that is sitting on the road at any instant, and it continually changes, so it's doing that. But that part of the tire is at rest with respect to the road for that instant. And the point of contact between a tire and a road is at rest. That lets the knobs on the road intermesh with knobs on the bottom of the tire, and by knobs I mean little tiny atomic projections meshing with each other, and that's static friction. So that's why we use static friction when we're dealing with a tire rolling along a road continually. If you try to slam on your brakes, nowadays nearly every car has anti-lock brakes, and so it kind of prevents you from doing that. But if you lock up your wheels so they're not spinning anymore, then you start to slide, those projections kind of get broken off, and you've got the kinetic friction, and the coefficient of kinetic friction is always less. So you don't want to slam on your brakes. When I was taking driver's ed, they taught us to pump the brakes. Push gently. If you start to skid, you let off. Push gently again. If you start to skid, let off. That's what anti-lock brakes do automatically. As soon as they start to detect that wheel starting to lock up, they back off a little bit. And if you slam on your brakes, you'll feel this dun 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 going on in your brake pedal, and that's the anti-lock feature preventing you from locking up the wheels. So this point is at rest instantaneously, but that means that when we're stopping a car, we're using static friction, and we're going to max it out because we want to know the shortest distance in which the car can stop. So, free body diagram. Stick it on the left side this time. We've got the weight of the car there. We'll have a normal force upward. It's a horizontal surface, and so this will be easy for getting that. And let's just suppose that the velocity of the car is to the right. That frictional force will have to point to the left to slow the car down. So here's our static frictional force there. The sum of the forces in the y direction here are going to equal 0. The car is not sinking into the road, and it's not jumping off the road. So those will equal 0, which just means well, let's see, I should pick a direction. I'll let y point up and x point to the right. That means n minus mg is going to equal 0. Up is positive. So I have that. Sum of the forces in the x direction will equal ma. and ma sub x. In this case, that's the only place we have acceleration. Well, the only force in the x direction is that F sub s. So F sub s is going to be in the negative direction, and that'll equal ma. Oh, I didn't solve this one out. The normal force in this case is just equal to the weight. So I can do that. Okay, well, F sub s, when that's maxed out, will equal mu sub s times n in magnitude. Actually, I've kind of got it taken care of with that minus sign there. And so minus mu sub s n equals ma minus mu sub s mg equals ma. So the maximum acceleration here that you can get in magnitude, it's just going to be mu sub s times g, but in this case it points to the left. So we'll have that. Well, what is the equation of motion going to look like in this case? Well, we'd have x equals x naught, we'll just let that be 0, plus v naught x t minus 1/2 mu sub s g, that's the acceleration, times t squared. So I could figure it out with this. I'll also have v sub x is going to equal v naught x minus at, but a is mu sub s g times t. Or, now, if I was to solve it using these, I'd want v sub x to be 0 when it stops, and I could solve this expression for the time. So I could get the time, and then I'd have to come back and plug it into this equation. But I'm lazy. I like to do things simpler. There's that other equation. There's v squared minus, or v sub x squared minus v naught x squared equals 2a delta x. And if I plug things in, at the end, v sub x is going to be 0. I'll have minus v naught x squared equals minus, a is negative mu sub sg, so it'll be minus 2 mu sub sg delta x, and delta x is how far it'll slide before it stops. So delta x here will equal v naught x squared over 2 mu sub sg. Notice how we're continuing to use those equations, one-dimensional equations of motion. It's a two-dimensional problem, but we split it into components, and we use these things again and again and again. All right, well, the problem is they gave me the speed in miles per hour, which is, that's okay. It's an example of a freeway speed in the United States. So I'm going to solve for that. V naught x is equal to 70 miles per hour times, let's see, I want to get meters per second, so 1,609 meters per mile. Actually, it's ridiculous to keep 4 sig figs on that because we've only got 1 on the coefficient of friction, so I'll just call it 1,600, and actually that's good to 3, but we'll just wing it. And there's only one significant figure on this as well, so 70, you don't know, do they really mean 70, or do they mean 65.1 or 74.9? Somewhere in there. All right. Anyway, get rid of the hours. 1 hour over 3,600 seconds. And we get about 30 meters per second, I think. Yeah, it is. It is as good as we can do. So, delta x will equal 30 meters per second squared divided by 2 times mu sub s was 0.3. Oh, notice that coefficients of friction are dimensionless. Something to keep in mind. And then I could actually use 10 meters per second squared in this case, but 9.8, I'll just use that. Let's see, 900 divided, well, let's just go ahead and do it. I get about 200 meters. It would actually show up as 150 meters, but something like that. Or, and the uncertainty is in this digit, it could be 100 to 200 meters in there somewhere, depending on just how you happen to round things off while you were doing the problem. But around 200 meters, which is about twice the length of a football field. That's pretty long, actually. And if it's dark and foggy and there's a deer that's crossing the road 200 meters ahead, you might not even see it. So be careful with that. Okay, we maxed out the friction again. We used this expression here to try to figure that out. So move on and try another. 8.54 kilogram hanging block connected by a string over a pulley to a 6.23 kilogram block sliding on a flat table. If the coefficient of sliding friction is 0.20, find A, the acceleration of the blocks, and the tension in the string. Well, let's draw a picture of this situation and see if we can figure this out. String over a pulley, flat table, we can deal with that. So presumably there's a floor down here somewhere. There's a pulley, cord passing over there. 8.54 kilogram hanging block. I'm just going to call that M sub 8 for the mass of that. And then up here on the tabletop we have a 6.23 kilogram block. I'm just going to call that M sub 6. And this is going to be a two-body problem. But let's see how it happens to work. I'll need to make free body diagrams for both of these things. Let's start with the M6. So I'll just see what the free body diagram looks like for that. Two easy forces. It's on a flat surface, so it's got mg and n here. Whoops, and that's m sub 6g. It's got that. It has a tension pulling it to the right. And I'm going to, excuse me, I'm going to label that as T sub 6. It's the tension that's acting on the 6 kilogram block. And there's sliding friction up here. The sliding friction doesn't refer to this thing. It's hanging in the air. But there will be a frictional force opposing that sliding. So let's just call it its sliding friction. That's kinetic. We don't use a subscriptive S for sliding. We use a subscriptive K for kinetic, implying motion there. The S is for static friction, no motion going on. Or at least no sliding going on. So there's the free body diagram for that thing. If I pick a coordinate system for that one where x points to the right and y points up, I can start off with the sum of the forces equals MA, and then if I do it for this particular problem, it'll be F sub k plus N plus M6G plus T6 those things are going to equal 0. If I just consider the forces in the y direction, those are going to be 0. Again, the thing's not falling through the tabletop and it's not jumping off the tabletop, it's just moving sideways. And so with the coordinate system I've got, with y being positive up, I'll have n minus mg is equal to 0. So the normal force in this case is equal to mg. Not always the case. If we've got a tilted surface, that won't be the case, but it is here. All right. How about the sum of the forces in the x direction? I'll have T6. Those are going to equal, by the way, MA6 for the acceleration of the 6 kilogram thing. I've got T6 pointing in the positive x direction minus F sub k is going to equal, oops, that's M6A6. I forgot my little subscripts there. Yep. Anyway, because I've got two masses going on. Okay. There's an expression, but I can simplify it further because that kinetic friction will equal mu sub k times n, which is going to be mu sub k m6g, and so that expression becomes T6 minus mu sub k m6g, and that will equal m6a6. Okay, our expressions are starting to get kind of complicated with these coefficients of friction multiplying the normal force and things like that. So you're going to have to be careful when you write these down, and every once in a while back up and look. I've caught myself forgetting to put some subscripts on some of these things at times already. So let's be careful with that. That's as far as I can get, though, just by considering that mass that's sitting on there. Now let's consider the hanging mass. We'll make a free body diagram for it. And it's got its weight, so that'll be m8 times g. It's got a tension acting upward on it, and I'm going to label that as T8. It's the tension acting on mass 8. Now, that particular tension will be the same in magnitude as that acting on the mass 6, but I differentiate between them because this thing points in one direction and that one points in another direction. So as forces, they're acting at different places and they're acting in different directions. So be careful with that. Now about this. If mass 8 accelerates downward, mass 6 will be moving to the right, and I want to pick a coordinate system so their accelerations will both have the same sign. So I'm going to let positive be downward for this particular mass. Okay, I can use a different coordinate system. In fact, I can do it so it's got x pointing to the right and y pointing down. I don't even need to use x's and y's here because it's one-dimensional motion. But if I do that, if downward is positive, I'll have m8g, the magnitude of that, minus t sub 8, and it's minus t sub 8 because t sub 8 is pointing in the negative direction in my little coordinate system here, and that'll equal m8a8. Okay, let's see. That should do it for getting started. Now I can make a couple of simplifications. when you have a low friction pulley, and on any problems you're given, that's the assumption. If it's not a low friction pulley, they'll say it, but we don't have the tools for dealing with those just yet. In fact, we won't deal with them in this class. If you take engineering dynamics, you'll kind of learn how to deal with some of that stuff. But anyway, something that we'll be able to say is that in magnitude, T8 is equal to T6, and I'm just going to call those T. So that'll simplify my expressions by quite a bit. And then something else is, these two things are tied together by a cord. So if this one moves an inch downward, this one moves an inch to the right. I shouldn't be using inches, but if this one moves a centimeter downward, this one will move a centimeter to the right. And they're tied together so they both have the same acceleration. The magnitudes and the directions and the signs of their accelerations are the same because I chose it to be that way. And that's just something I like to do, rather than having to write down the equations and then have to try and figure out, okay, do they both have the same sign of acceleration? Well, yeah, they do because I chose it that way. But A6 is equal to A8, and I can just call those A. So now those two equations that I have are going to look like this. I'll have T minus mu sub k m6g is going to equal m6a. So that's what that one simplifies to. And this one will simplify to, let's see, m8 times g minus t is going to equal m8a. All right, now I'm going to pull a stunt that we haven't done before yet, but I'm going to add these two equations together. I just looked at them and saw, hey, this will work. I want to know what the acceleration is first. Now, how can you do that? How can you add one equation to another? Well, something you learned early in algebra was that an equality was maintained if you, let's see, let me grab a piece of scratch paper. If you had something like 5x minus 3 equals 7. One of the first things you could do to solve this equation is add 3 to both sides, and it stays an equality when you do that. Okay, so add 3 to both sides and you'll get 5x equals 10, and then you can divide both sides by the same number and you'd get x equal 2. Okay? But you can always add the same thing to both sides. Well, I'm going to add m8a to both sides of this equation. Okay, that's all right, but since m8a is equal to this thing, on this side of the equation I'll use this version of m8a, and on this side I'll use m8a. And what I'll get is, when I add these together, I'll have t minus mu sub k m6g plus m8g minus t. Well, there's a t minus t in there. They're going to be gone. And so what I'll get is m8g minus mu sub k m6g is equal to m6a plus m8a. Okay, sorry about my convoluted things, but I'm working in landscape mode on my paper, so I can't just work straight down. Anyway, I can factor that right side, and what I'll get is m8g minus mu sub k m6g equals, both of these have an a in them, so I'll have a times m6 plus m8, divide both sides by that, so I'll end up with this. a scary looking expression if ever there was one. M8G minus mu sub k M6G divided by M6 plus M8. Okay, well, let's see. Now it'd be time to plug in all the numbers, and you'd have to wrap your parentheses carefully around the numerator and the denominator as you do this. But let's look at this expression. M8G, that's the weight of this thing. That's the force that's actually going to contribute to the acceleration, is the weight of this thing. The weight of this one's balanced by the tabletop, the normal force of the tabletop. But this one is the accelerating force, except it's having to work against this frictional force acting on the 6.23 kilogram block that's up here, and so it has to overcome that, and so the net force is the difference between those two forces, one that's working to accelerate and one that's saying put on the brakes. The total mass that's being accelerated is the sum of those two masses. So what we actually have here is kind of a net force on top and a total mass on the bottom. So that expression makes sense. All right, and something you want to do when you solve a problem like that is go back and reflect. Now, I'm not going to bother to put in the numbers on here, although I did calculate those. Well, maybe I didn't yesterday, I don't know. But at any rate, it's just plug and chug at this point. Then, once you know the acceleration, you can just come back to either one of these equations and solve them for the tension. In fact, I would deal with this one, I think, because if I write that down here, it'll be the easier one to deal with. I have M8G minus T equals M8A. And if I kick the T across and bring that thing back across, this will turn into M8G minus M8A is equal to the tension. And then I can factor this, and I'll have G minus A times M8 is equal to the tension. And then since you would have calculated the acceleration here, you just have a simple subtraction in here. You multiply it by the mass of the 8 kilogram one, 8.54 kilogram, and you'd have the tension. So that's the easy one to solve. The other one is a little bit more work, but not that bad. Okay, that was a fairly complicated problem. Let's see what might come next. A crate of eggs is located in the middle of the flatbed of a pickup truck. As the truck negotiates a curve in the road, maybe we should just say it's a flatbed pickup truck, because then if they slide off, there's a crate of eggs all over the road. But don't have to. Anyway, the curve may be regarded as an arc of a circle of radius. Hey, that kind of sounds like circular motion to me. That means even if the truck is going at constant speed, there will be acceleration. You'll be changing the direction of the truck, and in order to change the direction of that crate of eggs so that it'll have the same centripetal acceleration, it can't slide in the pickup bed, and so we'll have to have friction in the pickup bed to keep that thing behaving itself, the crate of eggs. So we've got a coefficient of static friction between crate and truck is 0.60. What is the maximum speed of the truck if the crate is not to slide? Okay, well, at least we've got a coefficient with two significant figures here, so we might be able to come up with some kind of an interesting answer. And let's see what it happens to be. Now, just as a sketch of this thing, I'll just draw an arc of a circle here, and we've got this pickup truck in here. Here's the windshield. Okay, here's our little crate of eggs in there. And then somewhere over here would be the center of curvature of this thing. And this radius of curvature is 35.3 meters. And something we're going to want to keep in mind is that the centripetal acceleration that those eggs are going to be experiencing, or hoping to be experiencing, so they don't all get crushed against the side of the pickup truck, is going to be v squared over r. So that's something that we want. Now, how about a free body diagram for that crate of eggs? Actually, if we look at the back of the pickup, we've got the bed of the pickup here, and well, actually they don't show that much. Anyway, here's the crate of eggs, and I don't know, that's what it looks like, but they're going to have a force toward the center of the curve in order to let them negotiate the curve. That would be the centripetal force needed in order to make that curve. So, free body diagram in this case will have the weight of the eggs downward. We'll have a normal force from the pickup truck bed upward acting on them. And we'll have a static frictional force that has to be toward the interior of the curve. If the eggs were to slide, they'd slide to the right side of the pickup truck bed, and the static frictional force has to oppose that by pointing toward the left side of the pickup truck bed. So that's what we have there. If I have y pointing up, and I'm going to let x point to the left. I don't know why I always tend to draw curve situations and downhill situations where I end up with x pointing to the left, but it's just the way I do things, I guess. Anyway, sum of the forces equals ma, the most generic version of Newton's second law. So we have that, and in this case that would be N plus F sub s plus mg is equal to ma. So that's the most general form of Newton's second law here, but we can break it down. Sum of the forces in the y direction, and then I'll write them as scalars. Nothing's going on in the y direction. Okay, the crate of eggs doesn't jump up out of the pickup, and they also don't sink through the pickup truck bed. As long as it's not too ancient and rusty, they won't anyway, and it doesn't say anything about that. So those are going to equal 0. So we'll have N minus mg is equal to 0, or the normal force in this case is just mg again. We'll deal with some slanted surfaces in the next problem, or some of the next set of problems anyway. Alright, so the normal force is that. In the horizontal direction, sum of the forces in the x direction, those are going to equal ma. And the only force in that direction is that frictional force, F sub s equals ma. We're interested in maxing out that static frictional force. We want to know the maximum speed of the truck if the crate is not to slide. So that means F sub s will equal mu sub s times n. That's the one that can in general be less than or equal to mu sub s times n. So we have that. And what else do we have? Oh, n is equal to mg, so this will be mu sub s mg, and I can say that mu sub s mg will equal ma. Hey, look, the masses drop out. I don't have to know the mass of that batch of eggs. So mu sub s g is going to equal the acceleration. We've actually seen that before in a horizontal situation. Maximum acceleration will equal mu sub s times g. But you need to show that because sometimes it may not be the case. Now, it's centripetal acceleration that we're talking about here. So that means that I'll have mu sub s g will equal v squared over r. And then v squared, solving for that, I'll get multiply out from underneath by r mu sub s g, or v will equal the square root of, let's just plug in the numbers now. R is 35.3 meters. Times mu sub s, which is 0.60, times g, 9.81 meters per second squared. And I know I've only got 2 sig figs, but force of habit. Multiply all those together, and you would end up with v equaling about 14 meters per second, which, if you care to do a unit conversion on that, multiply it by 1 mile over 1609 meters times 3600 seconds. For that, you'd find out that it's about 31 miles per hour. And so seems like kind of a reasonable speed. If you're trying to make a turn, you might have stuff sliding around in the back of your pickup bed if you're going at speeds like that. So, some introductory physics problems that have to do with friction. Actually, some introductory friction problems is what I meant to say.